Okay, we first walked through the deadlock detection algorithm when you have multiple instances of a resource type, and then in the next segment we took quite a detailed look at an example. We worked it out, and during the course of working out the example, we tried to understand logically also what was happening. But for the sake of completeness, I wish to just give you the logical explanation alone, hopefully concisely in this segment. So what's happening here is, at each step in the iteration, the initialization part I'm not explaining here because I spent enough time on it in the first video of these three parts, the first one where I discussed the algorithm. So I'm only going to talk about that steps 2, 3, 4 of the algorithm, the loop part where you keep looking for something, you increment something, and then the final condition. So that's what I'm going to be talking about here mainly. So at each step, you look for a process which has not been completed yet, finished of I equals false, and whose requirements can be satisfied with whatever is currently available and free. Requirement less than equal to work. So, or a request less than equal to work. So this is what I meant, right? So finished is an array which tells you which processes have been finished and which have not. So if it's finished, you put true. If it's not finished, false. And we obviously want to look at the processes who are pending, right? If someone's finished, some process has been finished, you don't care about it. You're not going to allocate resources to it again. So we are bothered about the processes which have not yet finished. That is why your checking condition includes finished of I equals false. And you should be able to allocate whatever is requesting for from your existing inventory, right? So for example, originally we have 7 instances of A, 2 instances of B, and 6 instances of C. But let us say at this point you have only 5 instances of A. Then if a specific process is asking for 3 instances of A, from this 5 you can allocate. But if it is asking for 6 instances of A, then at this point you cannot allocate, right? I hope what I'm saying makes sense. So overall you might have so many instances, but some of them are already allocated to someone else. So you have only a few instances currently available in your inventory. So you're looking for a process which is pending, unfinished, and also one whose request can be satisfied within what is available to you at the moment. That is why request less than equal to work. Right, next, moving on. If such a process is found, we allocate its requirements, execute it, then you take back all the resources. So what happens is your first allocation plus equal to requirement, so or request. So whatever it requested, that you give it to the allocation. Then this is the this statement you will not find it in the algorithm. I'll tell you why. I actually did mention this in the example. Where was that point? This one? No, here. Yeah, so if supposing let's take this place. So this one is requesting 1 unit of A. Then I said from this 3 you take 1 unit and you will give it to the T3 process. So this allocation becomes 311 and this becomes a 213. So if you watch the segment where I did the example, I spent quite some time talking about this. So that is what I mean when I say allocation plus equal to request. But why do you not see this line in the algorithm? Because as I said, whatever is given is taken back, and then whatever was pre-existing is taken back. So whatever was given was taken back, that just becomes a plus something minus same thing, right? So in order to not complicate things, we don't do that. I've just put this here because I don't want you to randomly wonder why are we randomly taking work and adding it to allocation. What is the physical meaning behind that is, it asked for something, I am capable of providing that something from my existing inventory. So I am giving that, then I am taking that back, then whatever it had initially, that also I am taking it back. So whatever it had under allocation, that also I am putting it into work. Allocation becomes a 0 and finished is set to true. So what's happening here is, it asked for something, I gave it, I took back what I gave, and I also took back whatever else it had. Now you keep repeating this until all processes are done or until the loop breaks. So if at some point you are unable to find a process that satisfies both these conditions, then as I said, you check the finish array. If every value inside the array is true, it means no deadlock, you found a safe sequence. Whereas if there is an unfinished process in the queue, meaning some value of finish is false, but because this condition is not satisfied, you're not able to find any process. That means there is a deadlock. So again, what is the physical interpretation of this? There is an unfinished process, but it is asking for some resources right now, and you are not able to allocate those resources because you do not have them. See, if this happens at some intermediate point in the loop, that is fine. Like if you see, we did T0, 1, 2, 3, 4, T0 we finished, then when you came to T1, it did not satisfy the condition. Wait, let me show you the page. See, here it did not satisfy this condition. So we went to T2, T3, T4, then when we came back to T1, it satisfied, we finished. So that problem happening at an intermediate level is fine. But if it happens at the end and you have no other process which you can go to, there is no process which is satisfying this, you are forced to break the loop. It means there is nothing else you can go, there is no other process you can finish before this and come back to this, and you do not have what is necessary for this person to execute. It means you are stuck, right? This one needs something, you don't have it, there is no other place from which you expect to get something in return. So it's like, what do I say, you owe someone money, you don't have money right now, but if you've lent someone else something in the past, you can expect that person to give it back to you, so you will use that money to repay this person. If nobody owes you anything and you owe this person someone, then you are in a spot. That is the kind of situation here, and that indicates the presence of a deadlock. So that is what this algorithm physically stands for. That's the interpretation. So yes, that is that, and this is a quick food for thought kind of a question. So this is basically the initial conditions for the example we've been looking at ever since we started dealing with deadlocks. Those two processes P0, P1, two resources S and Q, one instance each. So assume you have only one instance each. This algorithm works in that case also. So multiple instances is basically an extension of single instance, right? So it's the same thing. You looked at it in the form of a resource allocation graph so far. Here I've given it to you in the form of these tables. So if you use the above, you know this condition leads to a deadlock. We've been through that multiple times in multiple contexts. Now if you use the same algorithm, the same logic, you are expected to arrive at a situation where you're not able to find any process and there are unfinished processes. That indicates the presence of a deadlock. So I would encourage you to try out this example, a very simple example I've chosen. Two processes, two resources, to understand how the algorithm works. So yeah, that's that. Thank you.